I am AKB Anjan Kumar Bhuiya from the Department of Mathematics, Vishwabharati. Today we start field theory. This is the first module. Here we will not go into the details of the Galois theory. We study only the field extensions, and as applications we characterize finite fields and give proofs for the three famous impossibilities: trisecting an angle, duplicating a cube, and squaring a circle. These three problems were posed by the Greeks before thousands of years. Here I would like to create your attention to the interesting fact that here we give the proofs of these three problems which are geometric in nature, but our proofs are purely abstract algebraic. Anyway, let us first develop the extensions of fields. In the first module, we characterize the extensions of a field, simple extensions, degree of a field extension, and tower rule. Recall that the complex numbers are defined as ordered pairs of real numbers. Thus, if alpha is a complex number, then it belongs to the set the Cartesian product R cross R, and so in its strict sense R is not a subset of C. Still, the field of real numbers is considered as a subfield of the field of complex numbers C. By identifying each real number A with the complex number A0. What is the justification in doing so? Actually, this is done in the sense of isomorphism. That means, the mapping F from R to C defined by F A equal to the order pair A0 is a monomorphism. That is, R is isomorphic to F R, which is equal to the set of all ordered pairs of the form A0, where A is a real number and this is a subfield of C. Thus, actually R is not a subfield of C and R is isomorphic to a subfield of C. Thus, we define extension of fields or field extensions as follows. Let F and K be two fields. F is called an extension or a field extension of K if there is a monomorphism F from K to F. This is denoted by F by K. Here we have a simple characterization of the monomorphisms F from K to F. Since K is a field and a field has no ideal other than 0 and itself, every homomorphism F from K into F is either a 0 homomorphism or a 1 to 1 homomorphism, because kernel of a homomorphism, a ring homomorphism, is an ideal. Thus, F is a field extension of K if and only if there is a non-zero homomorphism F from K to F. Now, we give an example of an extension of R. Consider the polynomial x square plus 1 over R. Since this is irreducible over R. So, the quotient ring F equal to R x by the ideal generated by x square plus 1 is a field, and the elements of this field are f x plus ideal generated by x square plus 1, where f x is an arbitrary polynomial over R. Now, we simplify the expression of an arbitrary element in F using division algorithm. Since R is a field, by the division algorithm for every f x in R x, we have some q x and a plus b x in R x, such that f x is equal to x square plus 1 into q x plus a plus b x, and hence f x minus a plus b x belongs to the ideal generated by x square plus 1, which shows that the element f x plus ideal generated by x square plus 1 is identical with the element a plus b x plus ideal generated by x square plus 1. Thus, we have the field F as the collection of all elements of the form a plus b x plus ideal generated by x square plus 1, where a and b are two real numbers. Now, to show that this field F is an extension of R, we have to define some monomorphism F from R to F. Define F by f a equal to the coset of A, that is a plus ideal generated by x square plus 1. Then it is easy to verify that F is a homomorphism. Now, to show that F is 1 to 1, for this consider A B in R such that f a equal to f b, which implies that a minus b is equal to x square plus 1 into q x. If a minus b is non-zero, then comparing the degree of the expression in both sides, we reach at a contradiction that 0 is greater than equal to 2. Hence, a minus b must be equal to 0, that is a is equal to b. Thus, f becomes a monomorphism and f an extension of R. It is interesting to note that this field f is isomorphic to C, and the an isomorphism can be defined as sigma a plus b x plus ideal generated by x square plus 1 is equal to a plus I b. Now, we give an example of an extension of Q. For this, consider the irreducible polynomial x square minus 2 over Q, and consider the field f is equal to q x by ideal generated by x square minus 2. As in the previous example, using division algorithm, we also have the form of the elements of f as a plus b x plus ideal generated by x square minus 2, where a and b are two rational numbers. Similarly, we define a mapping f from Q into the field f by f a is equal to the coset of a, that is a plus ideal generated by x square minus 2. Then f is a homomorphism. Now, we check the one-to-oneness of f in a different way. Here we show that f is not a zero homomorphism, and hence it will follow that f is 1 to 1. For this, it is sufficient to note that 1 is mapped under f into the coset of 1 that is 1 plus ideal generated by x square minus 2, not 0 of the field f, and hence f is a non-zero homomorphism. Thus, f is a monomorphism, hence f is an extension of Q. Here also you can note easily that f is isomorphic to Q root 2. Now, we give two examples of fields which are not extensions of any fields, in other words which has no subfield, that is proper subfield. Our first example is the field of all rational numbers Q. Let K be a subfield of Q. We show that K is actually identical with Q. Since K is a subfield of Q, 1 belongs to K, and so minus 1 is also in K. This shows that for any non-zero integer A, we have A equal to 1 plus 1 plus so on plus 1 A times if A is greater than 0, and A is equal to minus 1 plus so on plus minus 1 minus A times if A is less than 0. This shows that whatever it may be the non-zero integer A, always A belongs to K, also 0 belongs to K. Thus, Z becomes a subset of K, and which implies that the field of all rational numbers Q, which is the quotient field of Z, becomes a subset of K. Also, K is a subset of Q, thus K becomes identical with Q. Our next example is the ring of all integers modulo A prime P, that is ZP. If K is a subfield of Z, then 1 belongs to K, which implies that for any A in ZP, A is equal to 1 plus so on plus 1 A times, and hence A belongs to K. Thus, it follows that K is equal to ZP. We call such fields prime field. Thus, formally a field K is called a prime field if it has no proper subfield. Thus, Q and ZP are prime fields for any prime integer P. Now, we show that up to isomorphism, these two are the only prime fields. For this, first we show that every field F is either an extension of Q or an extension of ZP for some prime P, depending on the characteristic of F. If characteristic of F is 0, then we show that F has a subfield which is isomorphic to Q, and if the characteristic of F is a prime P, then we show that F has a subfield which is isomorphic to ZP. For this, first let us define a mapping F from Z into F by Fn equal to n1. Here n1 means sum of 1 n times when n is greater than 0, sum of minus 1 minus n times when n is less than 0, and this is 0 when n is equal to 0. Then F is a homomorphism. Now, either characteristic of F is 0 or it is a prime P. First assume that characteristic of F is a prime P, then we have P1 is equal to 0, which implies that P belongs to the kernel of F, and so kernel of F is non-empty. Since car f is an ideal of Z, so it is of the form mz for some m greater than 0. We show that m is actually equal to p. For this, note that image f is a subring of f with unity, and characteristic of image f is same as the characteristic of f equal to p. Then image f is isomorphic to Z by car f by the first isomorphism theorem. Again, car f equal to mz implies that Z by car f is isomorphic to Zm. Thus, image f become isomorphic to Zm. This shows that characteristic of image f is equal to m. Again, we have characteristic of image f is equal to p. Thus, m is equal to p and image f becomes isomorphic to Zp. Thus, f has a subfield which is isomorphic to Zp. Now, assume that the characteristic of f is equal to 0. In this case, kernel of f contains only the 0 element, and so f becomes 1 to 1. Since f is 1 to 1, fb is non-zero for all b not equal to 0, which helps us to define a mapping psi from Q into f by psi of a by b is equal to fa into fb inverse. Again, note that fb is non-zero, so fb inverse exists in f. You can check that psi is well defined, psi is 1 to 1 and psi is a homomorphism. Thus, we get Q is isomorphic to psi q, that is image of psi, which is a subfield of f, and thus the result follows. And as a corollary, it follows immediately that if f is a prime field, then f is isomorphic to q if characteristic of f equal to 0, and f is isomorphic to Zp if characteristic of f equal to p. How does it follow? Suppose f is a prime field and characteristic of f is equal to 0, then it follows by the previous result that f has a subfield which is isomorphic to q. But since f is a prime field, it cannot have any proper subfield, and thus it follows that q is isomorphic to f. The similar case is for 2. Thus, we have defined an extension of a field, give examples of field extensions and examples of fields which are not extension of any other fields. Now, we characterize simple extensions. The motivation for introducing simple extensions is to express an extension f by k by an element c in f and the set k. Since intersection of any collection of subfields of f is a subfield of f, given any n elements C1, C2, Cn of f, we can find the smallest subfield of f that contains k as well as all of C1, C2, Cn. This particular unique subfield of f is said to be generated by C1, C2, Cn over k and is denoted by this symbol k C1, C2, Cn. In particular, if n is equal to 1, then we get kc, which is of our special interest. We define an extension f by k to be a simple extension if there is some c in f such that f equal to kc. Now, we express the elements of kc in terms of c and the elements of k. Since kc is a field and c belongs to kc, we have c, c square and so on, all are in kc, and hence kc contains the elements of the form k0 plus k1c plus so on plus kn c to the power n. This is actually fc, where fx is a polynomial in kx, that is kc is equal to set of all fc, where fx is a polynomial over k, becomes a subset of the field kc, but in general kc is an integral domain, not a field. Since kc is a field, it should contain fc inverse for all non-zero fc in kc. Finally, it follows that kc is equal to fc into gc inverse, where fx and gx are two polynomials over k such that gc is non-zero. Thus, actually what we have proved is that kc is the quotient field of the integral domain kc. For example, consider q root 2, that is the field generated by root 2 over q, precisely the subfield of R generated by root 2 over q. Certainly, the elements of this field are of the form f root 2 by g root 2, where fx and gx are two polynomials over q such that g root 2 is non-zero. If fx is a polynomial, say a0 plus a1x plus so on an x to the power n, then f root 2 takes the form a plus b root 2. Hence, g root 2 is also of the form c plus d root 2. Thus, if alpha is an arbitrary element of q root 2, then rationalizing a plus b root 2 by c plus d root 2, we get alpha in the form r plus s root 2 for some rational numbers r and s. Conversely, for any r s in q, r plus s root 2 belongs to q root 2. Thus, we have q root 2 to be the set of all elements of the form a plus b root 2 for some rationals a b. Now, we show that there may be field extensions which are simple, but not explicitly in the simple form. For example, consider q root 3 root 5. Actually, this is a subfield of R generated by root 3 and root 5 over q. So, it seems that it may not be a simple extension since it is generated by two elements, not by a single element. But now we prove that we can find an element in q root 3 root 5 which generates this field over q, and hence it follows that this is a simple extension of q. Note that both root 3 and root 5 are in q root 3 root 5. Since q root 3 root 5 is a field, so it follows that root 3 minus root 5 belongs to q root 3 root 5. Again, q root 3 root 5 is the smallest field that contains q and root 3 minus root 5. So, q root 3 minus root 5 is a subset of q root 3 root 5. Now, root 3 minus root 5 belongs to q root 3 minus root 5 implies that the inverse of root 3 minus root 5, that is 1 by root 3 minus root 5, belongs to q root 3 minus root 5. But 1 by root 3 minus root 5 is equal to minus half of root 3 plus root 5, which also belongs to q root 3 minus root 5. A simple computation shows that both root 3 and root 5 belongs to q root 3 minus root 5, and hence q root 3 root 5 is a subset of q root 3 minus root 5. Thus, it follows that q root 3 minus root 5 is a simple extension generated by root 3 minus root 5. Please check yourself that root 3 plus root 5 is also a generator of the field q root 3 root 5 over q. Just like the field of all complex numbers C is a vector space over the field of all real numbers, if f by k is an extension, then f becomes a vector space over k. And we know that every vector space has a basis and hence has a dimension. Thus, we can associate a positive integer n to every extension f by k, which we call here degree of the extension. Let f by k be a field extension. Then the multiplication in f induces an external composition k cross f into f, and it is easy to check that this external composition satisfies all the following 4 properties. Actually, the property 1 and 3 are nothing but the distributivity of multiplication over addition in the field f, and the property 2 is the associativity of product in f, and the 4th property is the property of the unity. Thus, f becomes a vector space over k, and we define the dimension of f as a vector space over k to be the degree of the extension f by k, and it is denoted by this symbol, which we call f over k. Since the field of all complex numbers is a vector space over R of dimension 2, so the degree of the extension C by R is 2. Similarly, the degree of the extension q root 2 over q is 2. We call an extension f by k to be finite if f over k is finite, otherwise f by k is called an infinite extension. Since real numbers as a vector space over the field of rationals is an infinite dimensional vector space, so R by Q is an infinite extension of fields. Now, we have a very important theorem which is known as the Tower rule, which proves that if f by L and L by K are two finite extensions of fields, then f by K is also a finite extension, and the degree of the extension f by K can be expressed as the degree of the extensions f by L and L by k. Actually, the degree of the extension f by k is the product of the degree of the extensions f by L and L by k. Also, this theorem suggests a basis of the extension f over k. Here I give only a sketch of the proof. Suppose f is a finite extension of L and L is a finite extension of k. Assume that the degree of the extension f by L is m and a basis is u1, u2, um. Also assume that the degree of the extension L by k is n and a basis v1, v2, vn. Then you will get a detailed proof in the E content of the result that u1 v1, u1 v2, so on u1 vn, u2 v1, u2 v2 and so on u2 vn and so on um v1, um v2 and so on um vn becomes a basis of the vector space F over the field K, and thus it follows that the degree of the extension F by K is m into n, and hence the result follows. Thus, in this module we have introduced the definition of field extensions and the important idea like degree of an extension. In the definition of degree of an extension, we have used the very intrinsic feature of being F a vector space over K, and for F to be an extension of K, you recall that it is not necessary that K is a subfield of F. It is sufficient that there is a monomorphism from K into F